Hi, this video is on the extended GCD, or the so-called Euclidean algorithm, which is actually a good thing to study in an algorithms class because I read somewhere once that it's the oldest published algorithm, or oldest thing that anyone recognized as an algorithm. But we're interested in it. We want to be able to get special numbers, let's call them K and D, such that we can get 1 is equal to K phi plus DE. And that's the magic thing that we need for RSA. So the number D, as we saw in the previous video, is what we need to be able to decrypt. And you can only get this magical D if you can get phi, which requires factoring n, which is p times q. So what we're focused on here is using the GCD algorithm with some extra feature to come up with the magical numbers K and D. So often when people talk about the greatest common divisor algorithm or the Euclidean algorithm, they just talk about finding the greatest common divisor. But for us, that will always be 1, because we're going to actually take E to be a prime number, and it'll almost never be have a common factor with phi. Okay, so the big fact here is old-time, something we'll use a lot, is old-time integer division, like you might have learned in elementary school. So if you take number A and divide it by number B, eventually you'll get a quotient Q, and when you multiply back down, the usual stuff, you end up with the remainder R. And the way to write that is A is equal to QB plus R, where 0 is less equal R is less than B. Okay. So it turns out this relationship between two numbers A and B lets us get the GCD by a reduce and conquer. So technically, this is not the divide and conquer. Divide and conquer implies you're breaking a problem into 2 or 3 or 4 subproblems that are about the same size. Reduce and conquer, typically you just whittle the problem down a little bit on each recursive step. So, but it turns out to be enough here. So the key reduce and conquer idea is that the GCD of A and B is equal to the GCD of B and R. And we'll prove that as follows. So if D divides A and B, then what? Then clearly D divides B. Oops. I better clean that up. Sorry. All right. D divides B. And since D divides A, let's see, R from this fact up here, R is equal to A minus QB. So clearly D divides A and B implies D divides R. If D divides A, that means that R is a factor of A, and it's also a factor of B. Then we can just factor D out of each of these and get it. And more specifically, that means that A is equal to some V times D, and B is equal to some W times D. So we can pull out the D, and D, so R is equal to D times something, some integer. Okay, and the converse is, so that shows that any number that divides A and B also divides B and R. And if D divides B and R, then D divides B. And since A is equal to QB plus R, so same argument, D divides B and D divides R, then obviously D divides A. So what we've proven is that D is a factor of A and B if and only if it's a factor of B and R. So that means the greatest common divisor that A and B has is the same as the greatest common divisor of B and R. Okay. So that was a little boring and technical. But so let's, the amazing thing is this one, it's so important I'll put it in red. This one observation actually is our whole algorithm. So let's go to another page. Okay, so here's how we set it up. So this is going to be, I'm going to write this, everything we're going to do here in a minute for the extended GCD example, all on this one page. So we're going to start with A and B. So these are the two numbers that we want to get the GCD of. So I'm going to do this in the same example as in the notes. So you might want to see this is out of the rsa.pdf document for the pre-reading if you want to, if these lovely videos aren't enough for you. So we want to take the GCD of A and B. And to do that, we have a, basically the order of this is debatable. So we're going to compute the quotient and the remainder. So we simply divide 1861 by 757. So let me do that here on my computer, my calculator, which is on my computer. So 1861 divided by 757 is 2.45 blah blah blah. So that means it goes in twice, and the remainder is 2.45. So I subtract 2 and multiply by the divisor, and I get 347 for the remainder. So this means that 1861 is equal to 2 times 757 plus 347, as desired. And now here's the whole algorithm. The B takes on the role in the algorithm of A, and R takes on the role of B. So maybe the Q and the R should be switched, but I'll leave it this way. So now we just have to divide 757 by 347. 757 divided by 347, oops, is 2.18. So I'll subtract the 2 and multiply by 347, and we get 63. So now we promote them again. So the GCD of 757 and 347 is the same as the GCD of 347 and 63. If I divide 347 by 63, I get 5.5 something. Subtract the 5, multiply by the 63, and the remainder is 32. And then we do 63 and 32. So I can do that almost in my head. Goes in once with a remainder of what, 31. And then this becomes 32 and 31. So that goes in once with a remainder of 1. And this is 31 and 1, which goes in 31 times with a remainder of 0. And then we promote 1, 0. All right, so at that point we're done. You'll see why I'm drawing these lines so aggressively in a minute. Just like to draw lines. Okay. So that proves that the GCD of my original numbers, 1861 and 757, is in fact 1, because all the GCDs all the way down are all the same. The GCDs of all these pairs of numbers all the way down are one equal to each other, and hence all equal to 1. Okay, I don't know why I'm doing this. Okay, so now that really is kind of fun, and it's a nice little algorithm, but that's kind of not the point. The point is that we really want S and T, say, with the property that, in this case, at 1861, S times 1861 plus T times 757 is equal to the GCD. Okay, so what we do is we work our way backwards. So we'll call this column S and this column T. So at the base case, it's trivial in this row to it's trivial to find them. So for example, I could take 1 and anything. So typically we take 0, because you can see that 1 times 1 plus anything times 0 is equal to 1, as desired. So now the problem is, how do we proceed? So we're going to proceed upward until we get the desired, recursively, until we get the desired values for S and T. I'll come back to this in a second. I don't know about a second. Okay, so we have to take a digression and come up with a way to go upwards line by line. So let's jump ahead to another page, and then we'll come back to this one. Okay, so back here, the formula says boost this, so this becomes 0, and this becomes 1 minus the t prime times the q. So t prime is 0, so it doesn't matter what this is. So this is just 1. And notice we should always, that's a terrible one, we should always check. So 0 times 31 plus 1 times 1, is that equal to 1? Sure. So those first few are too easy. So let's keep going. So this one will be 1. The s prime, the s is just the st prime. And this will be 0 minus 1 times 1. So this will become minus 1 in this spot. So sure enough, 1 times 32 plus minus 1 times 31 is equal to 1 as desired. So continuing, we get minus 1, and then this one will be 1 minus 1 times 1. And if you do the math correctly, the arithmetic correctly, that's 2. And sure enough, minus 1 times 63 is minus 63, plus 2 times 32, which is 64, gives us 1. So continuing, like, the numbers get worse as we go. So this is 2, and then this will be minus 1 minus 2 times 5, so that's minus 11. And we can check one last, oops, no we can't. So we're going to have to just take it on faith. This is also in the notes, the document, rsa.pdf, so you can compare. And I'll be doing that to make sure, oh, wait a minute. I've got the wrong thing. Never mind. No. What have I done? Oh, no, that's right. Okay, so next to last step, this gets promoted over to here, and this becomes 2 minus 11 times 2, so that I believe is 24. I'm just circling these to clarify what's the final number in each cell. And then we boost this up to 24, and this becomes minus 11 minus 24 times 2, so that's 48 plus 11, so it turns out to be 59. And we can check, and you should actually check on every single row as you're doing these. We can check that 24 times 1861 plus 59, here, let me put these in parentheses because it looks cool. 59, whoa, wait a minute. That's minus 59, of course. That's the problem. Minus 59 times 757. And I'll just do this to be honest. So in a little calculator, we take 24 times 1861 is, 24 times 1861 is 44664. 44664. And we have minus 59 times 757, which is 44663, which is equal to 1. Ta-da! Which is exactly what we wanted. Well, not quite. So this just worked out. There's a 50-50 chance that it'll work out for what we want. And the sad thing is, we wanted t greater than 0. If you look back, the way we're going to apply this in the RSA, so in the RSA we're going to apply it, we're going to use phi for A and E for B, and the numbers we're going to get are what I've been calling K and D. So we want the D at the top of the chart to be positive. So unfortunately it came out negative. So why did it come out negative? Well, it turns out, if you look down here, if we'd started differently, we might have been able to flip it. So it turns out, so there's nothing wrong with the 24 and the 15 minus 59, except for our purposes, it's easier to have this one end up being positive. So it just turns out you want to look in general, either 1 and 0 or 1 and 1 seem to work well, because the smaller numbers you use, remember we could use anything in this spot, so I'm going to use a 1. And the point of that is, then this becomes a 1, and this becomes, actually it becomes 1 minus 1 times the q, which is 31. Ooh, is that right? Minus 30? Yuck. Do I believe that? Yeah, I guess. So it's kind of unfortunate. But remember, you're only doing this by hand academically. So the check says 1 times 31 plus minus 30 times 1 gives 1. Okay. And the point is, once we have a number, this is going to go negative, positive, negative, positive, negative, positive. So the 1 makes the numbers blow up a little sooner, but it's worth it because we want to end up with a positive. Here, we could have seen it was going bad right about here. We could have said positive, negative, positive, negative, positive, negative, and said, whoops, no good. All right, so let's finish this up. So this will then be minus 30, and this will be 1 minus 30 times the q, which is 1, so it'll be 31. And let me just check that. So 32 times 30 is 960, and 31 times 31 is 961. So that works out. Okay, now we get 31, and here we get minus 30 minus 1 times 31. So that'll be minus 61. All right, I'm going to be brave and not check it. Now let me just check it. Okay, so 31 times 63 is 1953, and 61 times 32 is 1952. So that's looking good. So minus 61, and this will be 31 minus 61 times 5. Yuck. All right, so 61 times 5 is 305 plus 31. So it's 336. All right, I really got to check that one. So it's 61 times 347 is 21167. And 336 times 63 is 21168. I think that was good, right? Okay. All right, then we get up here. We're almost there, so bear with me. 336 will be minus 61 minus 336 times 2. So that number will be 336 times 2 is 672. Plus 61, so it'll be minus 733. All right, we're so close to the top, I'm not going to check that one. So we end up with minus 733 and 336 minus 733 times 2. All right, so 733 times 2, 733 times 2, oops, 733 times 2 is 1466. Plus 336, so 1802. All right, so the last check. So I think I can use the magic hand and scroll this up a little. Okay, good. Oops. So the check here is that minus 733 times 1861 plus 1802 times 757 is equal to, okay, so 733 times 1861 is, 1364113. Oh, and that is negative, plus 1802 times 757 is positive 1364114, which is in fact equal to 1. Yay. Okay, so these two different ways of doing it. we need the, so 1802, if we were doing RSA with 1861 as phi and 757 as E, then the 1802 would be the D we need to use to decrypt. Okay, so let's talk efficiency for a minute, because that's kind of a nice thing. Okay, so here's the idea. Let's remember how to do it. So let's look at the chart. So let's say at the chart at some point we have a number B and a number R, and we have S prime and T prime in our chart. And so we've got what we were calling A, B, R, Q, S, and T in the chart. And so what we're going to show is how to boost it one notch. So if we have B and R in these columns, doesn't matter what these are, and we've got these, so if we've got it, so we're assuming here that we have S prime times B plus T prime times R is equal to 1. So we want, and what we want to get is these guys for the numbers that I'll call A and B. Of course, we're also assuming that A is equal to QB plus R here. It's the relationship between these three numbers. Okay, so it's pretty simple once we get the right idea. And the right idea is simply to say that R is equal to A minus QB. And then we'll plug that in. So I got that obviously from this fact by subtracting QB from both sides. And I'm going to plug this quantity in for R up here. So what we have is S prime B plus T prime times A minus QB is equal to 1. So that's very natural algebra. If we have these two facts, we often kind of solve around with them. So that's the key idea. Now, so what? Well, this is S prime times B. By the way, these primes have nothing to do with derivatives. They're just numbers. And then it's T prime, so I'll multiply this out. T prime A minus T prime QB equals 1. And then it's just a matter of realizing that we've done what we want. We have multipliers of A and B. So the multiplier, the multiplier of A is just T prime. And the multiplier of B is S prime minus T prime Q. So this says, if we just call this number here Q, it says to boost these back up, this is T prime, so it just goes this way. And this is S prime minus Q T prime, or T prime Q. So we take this number minus this number times this number. So this takes some getting used to, but those are the formulas. So now let's go back to the previous page and see if we can fill into our chart. Okay. So for efficiency, you can read rsa.pdf if you want, and it proves something. It proves basically that the algorithm is good. It's good because we can do the GCD of absolutely huge numbers in fairly short time. So in fact, it turns out the worst possible A and B, worst in the sense of taking the longest number of steps, are Fibonacci numbers. And if we just do an example, so Fibonacci numbers are like 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. So if we take in our chart like A, B, Q, R, so if we take, like say 89 and 55, well, how many times does 55 go into 89? Well, it goes in 1, and if you subtract 59, the remainder is the next Fibonacci number down. So then when we do the GCD of A and B is equal to GCD of B and R, we get the next pair down. It goes in once, and the remainder is 21. And the next one is 34 and 21, which goes in once with the remainder of, 13. And then we get 21 and 13 goes in once with the remainder of 8. And then we get 13 and 8 goes in once with the remainder of 5. Then we get 8 and 5 goes in once with the remainder of 3. And we get 5 and 3 goes in once with the remainder of 2. And then we get 3 and 2 goes in once with the remainder of 1. And we get 2 and 1 goes in once with the remainder of 1. And then we get 1 and 1 goes in once with the remainder of 0. So we had to go all that way to get these. So in fact, it turns out these are the worst guys. So the size of these numbers, that's the most steps you can do. And you can see why in some sense. It's because Q is the guy that really, when you have a bigger Q, you really drop down the numbers quickly. So if Q is 1, it just crawls its way down. But even these cases don't take too long. And the reason for that is the Fibonacci sequence grows at a rate in theta of about 1.5 to the n. So the Fibonacci numbers grow exponentially, so you can get really huge Fibonacci numbers. Notice if you've got the Fibonacci numbers f sub n and f sub n minus 1, it's obvious that it sort of takes n steps. So the number of steps is 1.5 to the n, so the log of that, it's proportional to n. So for example here, this was the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this was f sub 10 and f sub 9. And it took, so f sub 10 is pretty big, and it took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it took roughly 10 steps to get the 10th Fibonacci number. And since they grow so quick exponentially, that means we can have like 300-digit Fibonacci numbers that we can solve in like 400 or 500 steps. So all of this is quite doable for the RSA encryption. So I think that's all I need to say. Thanks.